Welcome back everyone. This is another video for ECE23, Module 4 Performance Task. Introduction to Digital Communications. This is yours truly, Mr. Agabal, vs ECE3. At this video, the topic we discuss are DPCM, Differential Pulse Code Modulation, how DPCM technique functions, and give example. So, first, DPCM. Differential pulse code modulation is a signal encoder that uses the baseline of pulse code modulation but adds some functionalities based on the prediction of the samples of the signal. The input can be an analog signal or a digital signal. Differential pulse code modulation is a procedure of converting an analog into a digital signal in which an analog signal is sampled and then the difference between the actual sample value and its predicted value. Predicted value is based on previous sample or samples. Is quantized and then encoded, forming a digital value. DPCM code words represent differences between samples, unlike PCM where code words represented a sample value. Basic concept of DPCM. Coding a difference is based on the fact that the most source signal shows significant correlation between successive samples. So encoding uses redundancy in sample values which implies lower bitrate. Realization of basic concept described above is based on a technique in which we have to predict current sample value based upon previous samples or sample. And we have to encode the difference between actual value of sample and predicted value. The difference between samples can be interpreted as prediction error. Because it's necessary to predict sample value, DPCM is form of predictive coding. DPCM compression depends on the prediction technique. While conducted prediction techniques lead to good compression rates, in other cases, the DPCM could mean expansion comparing to regular PCM encoding. So next, we have here the DPCM transmitter. We have to describe how does a DPCM transmitter works. So we have seen here an adder, quantizer, encoder, another adder, and our prediction filter. So we have here some sample input, X sub NTS, prediction error, ENTS, quantized error signal, EQNTS, predicted signal, E sub NTS, EQNTS. So we have here some formulas. So it will be used on the next slide. So next, we have here a sample problem of how a DPCM transmitter works. So we have here input of 1.1, X NTS is our input, X sub NTS is our predicted signal, ENTS is our prediction error, EQ NTS is our quantized error signal, and XQ NTS is the addition of X sub NTS, our predicted signal, and our quantized error signal. So first we have an input of 1.1 passed through our adder. So we have here a predicted signal of 0. We have a prediction error of 1.1. Prediction error is from input signal minus predicted signal. So we have a prediction error of 1.1. And then quantized error signal is at standard label. So we have here 1 and we have here 1. So we have our 1.1 pass through here. Predicted signal of 0. 1.1 minus 0 equals 1.1. Quantized error signal is 1. So XQ is input from predicted signal and quantized error signal. So we have 0 plus 1. Next, we have an input of 1.2. So we have a current prediction signal of 1. So 1.2 minus 1, we have a prediction error of 0.2. Our quantized error signal is a standard label is equals to 0. So our XQNTS is 1 plus 0 is equals to 1. So Next, we have an input signal of 1.3. Our current predicted signal is 1. So 1, 1.3 minus 1. Our prediction error is 0.3. Our quantized error is 0. So xq and ts is equals to 1 plus 0 is equals to 1. So this step is repeated until our last input 1.7. So next we have here DPCM receiver or how DPCM receiver works. So first we have here ENTS, our input, decoder, and other, our predictor, a low pass filter, and our X sub NTS or predicted signal. So we have here our input ENTS 1, X sub NTS, our predicted signal is 0. So our XQ and TS is 1 plus 0 is equals to 1. So next we have here input of 0, predicted signal of 1. So our XQ and TS is 0 plus 1. So our XQ and TS is our input and our predicted signal. So we have here. So at this part, we have an predicted error of 1, input of 0. So 0. So 0 plus 1 is equals to 1. So next is 0. We have an input of 0, predicted signal of 1. So 1 plus 0 is equals to 1. So same step at till our last input of 0. So next, application of DPCM. This technique mainly used for speech, image, and audio signal compression. In images, there is a correlation between the neighboring pixels in video signals. The correlation is between the same pixels in the consecutive frames and inside frames. This method is suitable for real-time applications. Advantage of DPCM. Bandwidth requirement for DPCM is less compared to PCM. Quantization error is reduced because of prediction filter. Number of bits used to represent one sample values are also reduced compared to PCM. So that's the end of our discussion for DPCM or differential pulse code modulation. So see you at our next presentation, and that's all.